Hi, I'm Henry Segerman, and this is the Orbiform D4 by the Dice Lab, which is me and Robert Fathauer. So these are four-sided dice. Well, I guess they don't really have sides, but there are four numbers that can come up when you roll them. And because of the symmetry of the shape, those numbers come up equally often, and the dice are fair. And they roll in a much more satisfying way than ordinary D4 dice. Ordinary four-sided dice are regular tetrahedra, which don't really roll at all, they just stop. These wobble around in cool and unpredictable ways. They also spin really well. And they have a whole other trick up their sleeves, which is the reason we made them. They have constant width. Every direction you measure their width, you get the same answer, up to any differences coming from the manufacturing process. More on that later. If you put a book down on a few of them, you can roll it around, just like rolling a book around on some marbles. Here I've got a clear plastic sheet to roll them on, so you can see how they move. Perhaps the most well-known solid of constant width, after the sphere of course, is the Meissner tetrahedron. It's a sort of bulbous tetrahedron with three of the edges smoothed off. Those smoothings make the shape have constant width, but they also break symmetry. So if we made dice in this shape, they wouldn't be fair. Patrick Roberts found a solution to this, a constant width tetrahedron where all six edges are smoothed in the same way. Sean Bentley wrote about Roberts' smooth tetrahedron in this blog post at his company, Go Engineer. He also 3D printed some of them and realized that they would work as dice. I learned about all of this when Sean's 3D printed dice were featured on this YouTube video by Grand Illusions. And it's obviously a great idea, so with Sean's blessing, Robert Fathauer and I started thinking about mass-producing these constant width dice. Here's Robert rolling them and comparing them with ordinary tetrahedral four-sided dice. But then we realized that there's a potential problem with mass-producing injection-molded dice in this shape. After coming out of the mold, the dice are tumbled to remove extra material and smooth out the surface. This rounds off any sharp edges or defects, but it would also round off the sharp corners of the tetrahedron. Without knowing exactly how the amount of rounding depends on the geometry of the thing getting rounded, it's hard to say how this would affect the constant width property. But it seemed likely that rounding would not be good for it. So we went looking for a constant width shape with no sharp corners. The sphere certainly has no sharp corners, but it doesn't have the tetrahedral symmetry needed to work as a fair four-sided die. We found a shape that would work in this paper by Guilfoyle and Klingenberg. Their shapes are C2 smooth, which more or less means that the surface is smooth enough to differentiate twice. There are actually a few parameters to play with in their shapes. We 3D printed 3 different versions with varying amounts of roundness. Although it's fun, we decided that this one rolls a little too well, so we went with the middling amount of roundness of the 3. Finally, what about the name? We call it the Orbiform D4 because Orbiform is apparently the name that Euler gave to solids of constant width. Alright, that's it. Thanks for watching. Oh, and if you happen to be in Park City, Utah and need a locksmith, check out Park City Lock & Key. They were super nice and let me borrow the owner's grandfather's calipers for this video.